outside of phase change, like here, 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 all the energy is going into raising the temperature. Q equals mc delta T, right? It governs these aspects. So down here, by the way, if this is water, this is technically what down here?
Ice.
Ice is solid, right? So down here I have ice, right? And it's governed by this, delta Q equals mc delta T. And up here I have what? Liquid water, right? So this is liquid. And this too is governed by Q equals mc delta T. And up top?
Water vapor.
Steam, water vapor, gas, right? Steam, and that too is governed by Q equals mc delta T. Excuse me for smushing it all in. It's these in-betweens, these phase changes that are weird, because we keep pumping energy in, and the temperature doesn't go up one bit. Not at all, okay? Doesn't matter how much you pump energy in, right? It doesn't matter how quickly you pump energy in. It's not going anywhere temperature-wise. It stays right where it's at. Where's the energy going?
It's going and changing it from one state to another state.
Exactly. It's going into changing states. It's going into breaking bonds. Okay. It's going into breaking bonds. All right. The solids, the objects are close together. They're bonded together, so to speak. And so we're breaking those bonds. We're releasing that. That's where all the energy goes. Now, this might be kind of a weird concept to you, but at freezing, right? You can put a bunch of ice on a hot plate on a stove. It doesn't matter how high you turn that stove, assuming that you're stirring it, right? To try to keep everything doing it, keep the heat even. But it doesn't matter how hot you turn your stove. The liquid water, is going to be at 0 degrees Celsius, and the ice will be at 0 degrees Celsius. And it's going to stay at 0 degrees Celsius until every last bit of ice has melted, and we only have liquid water, and then it will start heating up again. But it's not going to stop boiling, okay? Whenever you're boiling, this might be a little bit more familiar, right? Whenever you're boiling water in a pot, the water and the steam is going to stay at, no matter what, 100 degrees Celsius until every last bit of water has been converted to steam. Then we can continue to heat up that gas. Yes?
One time there was a student that asked a question about what if the water from the ice melted, gets away from the ice, won't it heat up after?
Okay,
What's the answer to that question?
if it gets away, right? Or let's say you're not stirring, I guess would be the idea, okay? If you're not stirring, then the heat might not be distributed evenly, okay? And we can get hot spots and cold spots, all right? So the water might heat up while the ice and the water around it is still at 0 degrees Celsius. That's possible. But kind of our idea here is we want everything to be distributed evenly. We want to keep everything even. We want to prevent hot spots and cold spots. We want to stir, right, to make sure that everything's operating together in one. And I mean, heck, we could attach a pipe to it, right, pump all the water away from the ice and then heat it up somewhere else. Of course we'd be able to heat it. By that time it's been removed from the ice completely. All right, but if the ice is there together with it, everything's evenly distributed, then it's going to stay at 0 degrees Celsius. Was that the story that you just told specifically you? Were you the student? Possibly. Okay. And was right now when it was happening? Probably. Okay. It happened when? Oh, gotcha. Okay. Evaporation and boiling. What's the difference between evaporation and boiling?
Evaporation just happens when it's at liquid, anytime it's at liquid, not necessarily at a boiling temperature.
All right, so temperature is difference between them, right? There's a temperature difference going on. I mean, the water...
At boiling, it's at 100 degrees, so it's automatically going with evaporation. It just doesn't naturally, even though the temperature is. So,
Yeah. Boiling, well, let's think about this in terms of temperature. What is the definition of temperature, somebody? Good. Measure of average kinetic energy of all particles. Now, we can think of temperature, how hot something is, to how fast it's moving. Okay, so whenever you have something that is boiling, right? So I have a container of water, and it is boiling. Forgot it doesn't work. So it's going to be red water. That means out of all these particles, the average equals 100 degrees Celsius. Good enough to break away on average. Now there might be some a little bit above, and if it's at 100 or above, that means it has enough energy to get out. Okay? It's going fast enough. It can get a running start, so to speak, and escape. And our average is high enough that all of them, on average, have enough energy to get out. That's the idea of boiling. Right? Now, evaporation.
Some of them are above.
Yeah, some are above the average. If our temp, let's say, is 40 degrees Celsius, you've heated it a little bit, maybe it's been out in the sun, something like that. Well, some of them, might have, if we think about the temperature of individual particles, which is an incorrect idea, it's still the average of all of them. But if we think about the temperature of an individual particle, one particle, because this is an average 40 degrees Celsius, right, an average kinetic energy, might have a 50 degrees Celsius. And this guy down here might have a 30 degrees Celsius, and this guy over here, because it's a average, could be at 100 degrees Celsius, and then you got a 20 degrees Celsius, and another 20 degrees Celsius, and it all averages out, right? It all averages out to 40 degrees. But one of those guys happens to have, by chance, enough energy to get out, right? I mean, this guy happens to have enough energy to escape. And so he heads on out because he happened to have enough energy just due to collisions and transferring momentum, and so he gets more velocity because a bunch of other particles happen to hit him at the exact same time, and so conservation of momentum happens, and out he goes. Yes?
Why don't they all uniform? Like, you think if you just left a fixed number of particles in place for a while, those are all non-uniformity uniform?
Eventually, right? Also considering that there are no other outside forces and that there's no other heat happening, everything's perfectly even, right? The problem is in our world nothing's perfectly even, right? The heat is distributed just by the sun and light in an uneven manner, right? You pick something up and you shake it, and although that's not much energy given to it, it's still a little bit. That's gonna manipulate it. So since nothing's even, right? Nothing is able to reach that perfect equilibrium. If it was in perfect equilibrium where everything was happy and everything was the same, yeah, it would be an evaporation. It just doesn't happen, right? It just doesn't happen at all. What are two ways? Oh, I should say this. Whenever that 100 degrees Celsius guy gets out, what happens to the average? What happens to the temperature? It goes down, right? Now, the 100 guy's gone, right? The 100 guy leaves out of here, leaving you with just a 50, 20, 30, 20, and all of a sudden our average is down somewhere around maybe 30 degrees Celsius. Right? That's why evaporation actually cools whatever it is, oddly enough. Okay, it actually cools. That's why you sweat. Okay? The idea behind sweat is you have liquid on your skin that is going to evaporate. Whenever the hot molecules evaporate off, now your skin is left cooling. Okay, so it cools whatever there is. Now, there are two main ways. There are a bunch of others. But two main ways, I guess we can talk about three, that we can make something evaporate quicker. What are they?
Pressure.
Pressure. What do you mean by pressure?
Decrease in pressure would allow for the part to become, I guess, less dense. Is that what I'm trying to look for?
Kind of.
Where it can pop out easier and you have less pressure to overcome the pop out. So
Yeah. Atmospheric pressure, how much pressure you're putting on it, less pressure means that guy has an easier time to head on out. That actually affects the boiling point too, right?
Right.
So, I mean, more pressure, this is why you use pressure cookers maybe. If your parents have one of those, they use a pressure cooker because the water doesn't boil at 100 degrees Celsius. They can get it up to 200 and 220 degrees Celsius if it's pressurized in there, which means a lot hotter, food cooks a lot quicker. Okay. And if we reverse it, for example, if you go up to Colorado, up in the mountains, Colorado, Denver, and higher up, the boiling point's, 85 degrees Celsius, 90 degrees Celsius, depending. Okay, 80 degrees Celsius in some places and lower, and so you end up having to cook your food a lot longer there. So yeah, pressure definitely. Okay.
It'll be like they like mountain flour or something like that.
Okay, yeah.
Is that having anything to do with it?
I mean, not really. The grocery stores, they understand it's all a marketing scheme, okay, grocery stores. My favorite example of that is mountain water. Does anybody like that spring water, have to have spring water in the bottle? Anybody? Big fan of bottled spring water? Good, okay. Is anybody like anti-water out of the faucet? I hate the taste of water out of the faucet. A couple of you, I mean, lots of y'all probably have well water.
Depends on what.
Yeah, how about city water? I hate
No,
city water.
not like our water at my house.
Okay. All right. Now, for a long time, and you'll find people who they just have to have bottled water. That's all they're going to drink because it's mountain spring water. I forget what company it is, but one of the big companies now, they got their start by bottling. I believe it was Boston City Water. They took Boston City Water, they put it in a bottle, they screwed the lid on, and then they sold it for $3 a cart. And it cost them that exact same cart, not even a penny, right? Because they're getting it straight out of the faucet, right? I mean, it's not. Technically, it came from a mountain, right? It hit a mountain, it flowed down, we got into the reservoir, it got pumped through the pipes after getting treated.
And
It's
then
all
chlorine
marketing
and
scheme.
fluoride
Now,
got in.
sometimes what they're trying to say is it came from the mountains, there's not as much pollution up there, right? It's grown in more pure soil, or it flows and before it gets to the cities where there are more pollution, we bottle it then. So then they would say it's a little bit more pure. So what? It's not really that much more pure. All right, it's not really that
They
much
still
more.
put chlorine and fluoride in it.
They still put stuff in it. They still have to purify, make it more pure, right? They might not put as much in there. But then again, whenever you're talking about city water, unless you're at a city where they really, really struggle with their water treatment plant, the amount of chlorine and fluoride, or the amount of fluoride, the amount of chlorine in it, is so small. I mean, it really, really is minimal. Okay? The same one. All right? Does that answer your question? So it doesn't have to do with pressure. It's all marketing. They're just trying to sell this stuff. That's their idea. How can we trick these stupid customers, consumers, into buying overpriced things? That's the idea. All right, so pressure, what else? Temperature, right? I mean, if we raise the average temperature, there's more of them near 100 degrees, there's more of them that can get out, right? If it's hotter outside, things evaporate quicker. That's good. One more. Surface area. Yeah, I mean, which is going to evaporate quicker. If I leave it like this, or if I make it like this. I mean, we can run the test if you like. See if it trip off.
Good job, Mr. Rich. Spillage.
Spillage. Won't spill.
Oh!
Rats.
Don't let it get on the...
We'll pull the rest of it here. Is it still starting to spill? Hold the edge. Huh? Draw pictures in it. Thank you later. Hold the edge, sir. Come on. Pull them all. Good. Okay. So, and I'll
Stay together.
about what it was, which is going to evaporate quicker rather than flash, which is going to have surface area matters, right? Because now there's more area for it to escape, right? Now the molecules, all the molecules, are closer to the surface. Does that make sense? If all of them are closer to the surface, that means they don't have to go as far to get out. Here, in the glass jar, if the guy at the very bottom has 100 degrees Celsius, that much thermal energy, where we would approximate them to be 100 degrees Celsius. Now, I'm being up front, I'm sure it's an average, and so this is an incorrect statement. Okay. Sure? Sure? I doubt it would. Sure, definitely. The guy at the very bottom, well, he has to get lucky enough to not run into all the other guys on the way up and transfer his energy to somebody else and maybe get it spread back out. Okay? So it requires a decent amount of luck. If it's pretty deep. It's pretty deep. If it's shallow, it doesn't require as much luck. That makes sense to everybody? Yeah. So there's evaporation and boiling. Yes, that is a statement. After that, we'll just see what happens there. We'll actually prove our statement. Latent heat. This is what y'all already talked about in chemistry. What's the equation for latent heat? Oh, come on. Give me a break. Come on. What's the equation for latent heat? Give me in form of Q equals ml. Thank you. Change in energy equals mass times this latent heat, L. Now there are two types of latent heats that we're going to deal with. Fusion and vaporization. Fusion and vaporization are the two types of latent heats we're going to deal with. Fusion specifically deals with what? Making it a solid or doing what, Drew? Melting. Good. You're going to use this for freezing and melting. Freezing and melting. Okay. And vaporization. Evaporation. And I'm going to generalize this to vaporization. It could come in the form of evaporation, how much energy continually has to be given to it, or boiling also. Vaporization. Okay. Or what else? Condensation. Good.
What else sublimation?
Condensation. Okay, now sublimation. What is sublimation, somebody? Solid. Okay, let's see. Sublimate means to go from a solid to gas, or gas to solid. Which is it? You're correct. Solid to gas.
Wait, I thought it that.
I'm sorry. What said that? Yep, it's just solid gas. That's sublimation. What is going from a gas to a solid? What's with a D? Desupplement. If I remember correctly, it's deposition.
Yeah, that's it.
I gotta say mitochondria.
You can think of it as a deposit, right? If that helps you remember it. It's being deposited down. It seems like nothingness in the gas plant. There it is. It's a solid. That would require different latent heat. Okay, that's going to require different latent heat. But we aren't going to deal with substances like dry ice that goes directly from solid to gas right now. But I could give you the latent heat, and it wouldn't be that big of a deal. Okay, it's going to operate the exact same way. Latent heat of sublimation. Yes.
What's going from gas to plasma?
What's going from a gas to a plasma, somebody? Plasmating? Nope.
Plasma.
All right, let's talk about this. What is a plasma? First,
Superheated gas.
superheated gas. It's so hot. Specifically, what's happening?
Is it breaking
It ionizes. Good. It ionizes. What does ionize mean? Yeah. To become an ion means you lose or gain electrons, and ionizing means it has no electrons. A plasma is a gas that's gotten so hot that all the electrons have been lost. Okay? So much thermal energy. Remember, thermal energy is in relation to how fast the objects are moving. So much thermal energy. The electrons, they're not going to hang on anymore. We can overcome Coulomb's law, and so off it goes. Okay, off they get. That's a plasma. Yes. I'm not saying you're crazy. I never said you're crazy. Sometimes people guess, but that's okay. So,
You're right.
correct.
Yeah, you're kind of having the...
Spilling. Other side. Ah!
Yeah, it's slowly like going that way.
Uh-oh. This might not work too well, huh? It's just going to spill all class period long.
The table is not perfectly level. What?
Yeah.
Gotta account for that error.
Yeah, it's a little bit of air right there, huh? Sweeping it over. No, it's not. There's still water on my hands. It'll evaporate, right? I mean, it's just distributed. We have even more surface area. So, latent heat QL, to kill a plasma, it's called ionization, because that's what you're actually doing. So you go from plasma to gas, a deionization, because that's actually what you're doing. You're deionizing. Okay? So,
Like it's like 1,500 degrees Celsius or something for water to become plasma.
very, very hot. I actually don't know. Very, very hot. 1,500. That sounds great.
You don't know?
Plasma, and you cooled it down, like took away without any electrons in the environment.
Yes.
So you got a plasma from
Yeah. We can pour plasmas at room temperature.
Sweet.
Awesome.
In fact, you've seen plasmas at room temperature. Gas station.
Oh, wait.
No, those are more lava lamps, kind of lava lamps. Now, think about those little plasma lamps where you put your hand on it and you see what's meant to look like bolts of electricity coming to your fingers and all.
Oh, that's awesome.
There's a little current that flows through that, okay, through the gas at that point in time, and then your fingers create a point for it to connect to. And so the electricity flowing through creates a plasma. It's just so cool at that point in time. There's not enough thermal energy traveling, but it's not a big deal.
So plasmas are visible?
Yeah. Oh yes, plasmas are very visible. The reason you see lightning is because the electricity is flowing through. Yeah, you can kind of see the spark, but the reason you see it so vividly is because when that bolt of electricity comes through the air, it superheats the air right around the column of electricity, turning the air into a temporary plasma. Thus the big flash, thus the really hot stuff, thus the melting cars and all that jazz. Not actually melting cars, melting rubber off the tire.
But the study from that the air directly around the plasma that is a lightning bolt is gets extra electrons just a little while, or like what happens?
Loses the electrons.
No, but the air that is the plasma,
Right.
the air right around that gets extra. It's like that actually goes.
Yeah. Yes.
And then just because of the natural like homeostasis of things, they go back to
Correct. 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 Now, here's the idea with heating. We heat up that column of air to the lightning bolt, really, really hot, right? And Q equals MC delta T. There's the amount of energy traveling through it, right? So that energy gets converted into thermal energy of the air, right? It heats up to some temperature hot enough to become plasma. And then you've got this big, massive, compared to this little column of air, the entire atmosphere is around it trying to cool it back off. So it's able to cool it back off like that. That's why the lightning bolt, you can kind of see the residual effects up there. That's not just in your eyes, that's real, okay? But it cools off. It's off.
So electricity is invisible. The only reason we can tell is because of the plasma then?
Yes, because electricity is just the flowing of electrons. And you're not going to see much of electrons flowing. Right, but they're teeny tiny. Right, but all the energy generally creates plasma. Yes. What makes a lightning bolt? All right.
Static electricity.
It's static electricity, and there are theories out there. Some of them are pretty good. The best theory is friction inside the clouds with water molecules and rubbing over each other. Okay, the steam, the gas particles rubbing over each other, creating friction, and then your negative charges end up at the bottom of the cloud, and positive charges end up at the top of the cloud. Now, another question would be is why does that happen, right? And I don't know. I mean, some things in our world.
Lightning goes from the ground up.
I'm sorry?
Lightning goes from the ground up.
Well, kind of. Some of it. Most of it goes from ground down, or from cloud down. Most of it. But a column is created. Some of the positive charges rise up.
I thought it was when Zeus got angry.
When Zeus got angry.
It's spelling again.
Okay, I swear to
Oh, okay. See, David Burris.
get off this computer. If you're not. All right. Let's run a few problems, Blake. Let's run a few problems, and then I'm going to probably give you a lot of time to work through today. Just because I want you to be able to run problems yourselves. Okay, number one, 5 ice cubes dropped into 977 milliliters of water at 39 degrees Celsius. What is the final temperature of the ice water? Now, we're going to make an assumption here, and we could prove our assumption wrong as we do the problem if we end up being wrong. We're going to assume all of the ice melts, just 5 ice cubes, right? So all of the ice melts into water. Now, ice, as it melts, is going to take in energy, right? That's how ice melts. It's taking in energy, and the water is losing energy. Thus, the water is decreasing in temperature, right? The ice particles, they're going to end up going up in temperature. So, the generalized idea here is Q needed, delta Q needed to change the ice into water equals the amount of heat that the liquid water loses. Now, I'm making an assumption here. I'm also making the assumption that as the ice melts, there is so little water from that just 5 ice cubes compared to the entire glass that it's not that big of a deal. We don't need to calculate Q equals MC delta T then to keep the water itself up from the ice that melted and get an equilibrium between the water that was already there and the water melted from the ice. Now, if you have a lot of ice in there, you would have to include that step in.
What you were dealing with a different compound that's actually more dense when it's frozen. So then when it melts, it'd actually be like a measurable change.
If you have a large enough measurable change, right, we're talking less than an order of magnitude difference, okay? Less than an order of magnitude difference, then we have to care about it. 5 ice cubes, though, each at 100 grams, or 110 grams. I guess these are big ice cubes, so my approximation is actually not too good on this one, but we're going to run with it anyway. In general, 5 ice cubes are going to be a lot smaller than that. The approximation is still good. Otherwise, like you said, if there is a measurable change, you would have to include, you'd have to run how much energy does it take to melt the ice, and then you remember us running Q equals MC delta T's for cold water and hot water being combined and coming to an equilibrium temperature. You'd have to do that step next. Okay. But we're just going to run this straightforward, neglecting the water that comes from the ice. So Q need to melt the ice. Well, I have Q is ML, right? But I need to put a times 5 out in front because there are 5 ice cubes, right? Each with a mass of 110 grams equals negative MC delta T, right? Good question. All right, think about what's happening with the ice specifically. It's melting, right? It's changing phase. So we're talking about the energy needed for phase change. Latent heat. Mass times the latent heat. Which latent heat we can use, by the way? Which one is that? Fusion, good. Yeah, we need to use that latent heat. Now, what's happening with the water? Is it changing phase? No, right? It's not changing phase. Stay in the same phase. It's still going to be a liquid. We're just cooling it down. Whenever you stay in the same phase, you're either heating or cooling, you're changing the temperature, use Q equals MCAT. Okay, the specific heat equation. All right, so this becomes 5 times 0.110 times latent heat of fusion. 3.34 times 10 to the what? Just 3.34? Oh, yeah. Should be big enough. Times 10 to the 5th, up at the top of that table. times 10 to the 5th. Units there are joules per kilogram. Joules per kilogram are the units for that. Equals a negative M. What's the mass of this water in kilograms? 0.997. 1 milliliter equals 1 gram, so mass 0.997. This is actually coming out really close in masses. This is nowhere close to order of magnitude. I should have to account for the liquid water coming together, but I'm still going to ignore it. Times specific heat of liquid water. 4.18 times 10 to what? Third. Times 10 to the third. And delta T is going to be T final minus T initial, 39. All right, so let's start working this out. What's the entire left side of the company? Punch that into your calculator. Give that to me again, please.
183,000.
700 equals 0.997 times 4.18 to the third. $4,167. Point what? 46. Okay, sure. What's my next step? Yeah, let's distribute here. I could go ahead and divide by 4,000. That'd be fine. In fact, why not? Yeah, that might make it easier. So sure, let's divide both sides by 4,186. So I'm dividing 4. Let's go ahead and let's get that negative out of the way too. 4,176.46. 46, right? So this is going to give me negative what? 44 point what? 08 equals TF minus 30. Add 30 to both sides. TF equals about negative 14. You should worry about stick figs there. Now, my fallacy in this problem, once again, is that there's too many ice cubes. Ice cubes are too big. What's actually going to happen in this situation? Is all the ice going to melt?
No, the water's gonna come.
Yeah. The water is going to be, the water is going to drop all the way down from 0 degrees Celsius, and they'll reach an equilibrium. You'll still have an ice cube or two left, but we can calculate how many ice cubes are actually there still. Okay? Calculate the amount of mass needed to bring the water down to 0 degrees Celsius. All right, let's move on to another one. How many 57-gram ice cubes would it be necessary to cool hot coffee, 98 degrees Celsius, down to iced coffee, 0 degrees Celsius? Assume that the specific heat of coffee is the same as water. There's your massive mug, 250 grams, and the specific heat of the mug. The mug's acting as the calorimeter. Okay? So why don't I give you a moment to try this? Now, you're going to see graphs that look like this all the time, and it's what I've already drawn, right? So 150 grams of substance shown below, heated by a 32-watt heater, substance, latent heat, fusion, what's the specific liquid, the specific heat of that liquid. So here's a graph that you're going to see all the time, and I've already talked about it. We're going to have to construct it for the previous problem. Okay, that's the idea, and then we'll do all the steps. So, going back down to this. For water, right, we set our graph of something like this. Right? Now, in this first part, we are starting all the way down at negative 12 degrees Celsius. Yeah? And we're going all the way up to steam at 120 degrees Celsius. There are 5 pieces. 1, 2, 3, 4, 5 that we have to include in this problem. You need the delta Q to heat up, to heat the ice. You need the delta Q to melt it. You need the delta Q to heat your water. You need the delta Q, vaporize it, boil it off, right? And then you're going to need the delta Q to heat the steam, okay? Add all those together, and you've got the total amount of heat that you had to put in. Okay, you got the total amount of heat you had to put in. So, what equation do we want to use for to heat up ice? What? What equation are we going to want to use to heat up the ice? MC delta T. We're not changing phases, right? Whenever you're not changing phases, you want to keep it the same. So to heat up the ice, you're going to use MC delta T. Well, let me try to write this out a little bit better for us. Q total equals. Possible. Q total is going to equal all those guys added up. Now for the ice, we're going to use MC delta T, right? And this is all ice, right? Now to melt it, what equation do I want to use? You know? And this is melting plus to heat the water. MC delta T, you see where we're going with this? And this is the water plus to vaporize it. ML again. And lastly, for the steam, MC delta T. A few things that you need to think of. What's the delta T for ice? Yeah, negative 12 up to 0, so the change in temperature would be 12, right? Temperature does not change during a phase change. What's the delta T of the water? 100. What's the delta T of our steam? 20, from 100 up to 120. Yes, Andy.
What is the latent heat of vapor condition?
Latent heat of...
exponent.
Say that again?
What's the exponent?
Fifth. Okay. Yes.
Now, when the ice is going from negative 12 to 0, does that kind of, for lack of a better term, sort of evaporate too? Because since that's still just an average, does some of it still go off, break off, and become water?
Okay.
Like liquid water melt?
Ice, yes. Ice does naturally have the same sort of deal as evaporation, just not as much so. Okay, because it's so much colder that the same effect of evaporation just doesn't happen as much, where some of it naturally breaks away. Okay, it's so much colder that they tend to stick, solid particles tend to stick very close to the average. They're tightly bound. Okay, so they tend to stick very close to the average, not with a couple of them getting so fast they're able to break away into a liquid. Mitchell.
Why is it that all the notation of specific heats and latent heats is really inconsistent? because you see a lot of time it'll just be a plain number, you know, like 450 or something like that. Sometimes it'll be in scientific notation, sometimes it'll be in engineering notation, like your vaporization there. And it's just really all over the place, like it'll be different every time. Sometimes it'll be like per Kelvin, sometimes per Celsius.
Numbers are numbers are numbers. You'll find this all the time. As you go through things, you'll notice that they're not, scientists aren't overly concerned with constants. A constant is just a constant, right? Whether it's in Kelvin or Celsius, we can convert back. Whether it's in this notation or that notation, we can convert back and forth. Who cares? Right? So constants, to be honest with you, in science, we use them all the time because we need them, but we care all that much about them. Not really.
Well, it just seems like a lot of other things are very standardized, but this one, at least in all the problems we've seen, is not.
Yeah. Sometimes they change it all up on you. Sometimes they change it all up on you. All right. Give that problem a shot.